so let's get started our second lecture, lecture 2. So in the previous lecture, we have considered a simple system called as SAP-1 instruction set, but whatever it is called, but anyway, it is just a calculator. And we have found that in order to implement this function, we have to introduce some logical functions. So among them, one of the most important one is of course binary adder and subtractor. But adder can be act as also subtractor with a minimal modification. So today I wanted to start from this binary adder. Okay. So if we are considering the sum of two binary numbers, then we can easily recognize that addition of two 1-bit binary numbers, that is sufficient to implement our, for example, 8-bit binary number addition. For example, when we have 1 0 0 0 0, and if we have another one like 0 1 1 0 1 0, let's say that this is 8-bit binary numbers. But when we try to make the sum of these two 8-bit multi-bit binary numbers, what we have to do is relatively simple. Just to consider the sum of these two numbers, and it will give us a certain number. And depending on their combination, sometimes we can have a carry bit, and sum of these three binary numbers will give us another sum, in this case 0, and will generate another carry. So we can just repeat this simple operation again and again, eventually get another 8-digit number for our result of addition. So although in general we need actually sum of three binary numbers. One is A and one is B, and the other one is C. So this C is sent from previous operation, so lower digit operation, and it is called as carry. So sum of these three binary numbers is done by a subsystem called as full adder. Here full means that we are considering also carry bit. But even this full adder can be implemented with just a sum of two binary numbers, and yes, sequentially if we perform this addition operation twice, then we can implement this full adder. So we are now just considering the sum of two numbers here, and even in this case we have to introduce carry bit. If we consider two different numbers called as A and B, then it can generate only 4 cases, because A can be either 0 or 1 and B can be either 0 or 1. So we have only 4 cases, and some of them, so all of them are shown here. Yes, 0 1 1 0, and here we have 1 carry bit. So it's not that difficult to understand. So if we include carry bit, so this is quite easy to have this way. So although 0 plus 0 should be 0, but that is interpreted as its carry bit is 0 and its sum bit is also 0. So we can now recognize in this way. Then it becomes just a logical function, and it becomes another logical function to calculate carry bit and sum bit. When you have a look at this carry bit, when do you have one value out of these four combinations. You can find that only when we have x equal to 1 and y equal to 1, when both of our two input bits are 1, then we have output 1. What is this? This is just and of x and y. So that is corresponding to our carry bit. And in the case of this sum bit, that is a little bit more complicated. It gives us just number 1, output 1, when one of our two input bit is 1. However, when both of them are 1, then we have just number 0. So this operation, logical operation, is called as exclusive or just to give us either one of these two x and y equal to 1, then it gives us just number 1 as an output. So if we consider ordinary OR, then we will have 0, 1, 1, 1 as a truth table. So that will be x or y, as you know. However, in the case of exclusive OR, we just exclusive the case where both of them are 1, so that becomes just 0, and that is shown as a sum bit of our binary adder. So this truth table is just shown here. So the main message of this simple discussion is that, okay, in order to make a computer, we need sub-blocks. Among many different sub-blocks, one of the most critical one is an adder, and even in this adder, we can consider just two logical operations: exclusive OR and AND operation. So if we can build any two input logical operation, for example, any operation, then we can try to build any kind of a logical system out of this bitwise operation. So now I wanted to say that our MOSFET is the building block to build such a kind of logical system. So if we have MOSFETs, not a single MOSFET, but if we have two different types of MOSFETs, then we can build a logical gate. So by combining those logical gates means that inverter or NAND or NOR or other things like OR and more complicated one, then we can build the complete combinational logic system. Okay. So this is today's main lecture. Start from what is the MOSFET. Okay, so I just wanted to say that nowadays the MOSFET is the basic unit of microelectronics. Sometimes you may discuss about alternative way to build microelectronic system, but frankly speaking, in practice there is no other alternative currently available. So this is the basic unit of microelectronics. Of course, we have other older technology like BJT or something like that. Yes, they are good, but when we consider just the volume of mass production, so the MOSFET technology, CMOS technology, is the only choice we can have. Okay, in this case, we have two different types of devices, typically called as N MOSFET and P MOSFET. And as we know, this alphabet N and this alphabet P are originally originated from, so negative and positive, and usually this N is reserved for something related with our electrons, and this positive is related with our holes. So because they are charged in a negative way or positive way, so that's the reason why we call it as N MOSFET and P MOSFET. Here we have N MOSFET, this is N MOSFET, and this is P MOSFET, their circuit symbol, and the difference is the position of these arrows. Or sometimes for P MOSFET we just introduce sometimes this bubble to represent that this is a P MOSFET. So but depending on the context, the meaning of N MOSFET and P MOSFET are quite clear, so you don't have to worry about that. And basically this device or these devices are controlled by gate contact. So gate voltage, its voltage controls the operation of this device. For example, when we have sufficiently high gate bias to this N MOSFET, then as all of us already understand, that will introduce a gas or electron. So that gas or electron will be used to conduct current. And in the case of P MOSFET, if we apply high enough gate voltage, it will be nothing. So the usual operation is usual operation. Okay, there was something wrong. Okay, the usual operation is usually we apply very low, relatively low voltage to the gate. In this case, we have a gas of holes, and this gas of holes will be used to conduct current also. So that's the reason why we have two different types of devices which act actually the opposite way to the input voltage. Yes, so for example, if we have a high enough voltage, then we can turn on this device. At the same time, we can turn off this device. Or if we have sufficiently low voltage, then we can now turn off this device. At the same time, we can turn on that device. Always they behave in a complementary way. If one of them is turned on and the other one is turned off, that is quite important to implement power efficient system. Okay. So therefore, in some sense, the existence of this P MOSFET is quite important for our silicon technology. So sometimes we can find many other alternative technologies whose electron dominant device outperforms the silicon one. However, in many cases, if you have a good electron device, then you don't have good enough hole device. However, fortunately, in the case of our silicon material, I don't know why, but we have more or less comparable devices, both operating in an electron way or hole way. So I think that is really good to have these two devices. Okay, anyway, although I'm talking about the basic of a MOSFET or something like that, but I assume that all of you in this classroom already understand the operation of a MOSFET. So I just try to start the discussion about its compact modeling. Okay, so although there are many different compact models, so how can we express the electric behavior of this device? but we are now talking about the simplest model, level 1. Who named this model or who numbered this level? But at the beginning of this industry, so some companies try to label or number those models. If the model is the simple, then usually they tend to number them, number those models with a lower number. And if we go to a more advanced model, then they try to give that model higher number. So it means that number 1 is the simplest model we can have in the real situation. But of course, this is no longer used practically. But I think that this is already good to have this model for educational purpose. And please note that many cases you can find some expression for N MOSFET, and for P MOSFET that is just understood. You have to find out the correct sign, because sometimes N MOSFET and P MOSFET have different polarities. So in many cases, just to introduce negative sign to your equation, it is okay to have a good enough expression. But please be careful, because for example, sometimes the component like lambda, that is a positive value for N MOSFET, and if we follow just sign difference between N MOSFET and P MOSFET, then we have to have negative lambda value for our P MOSFET. But by convention, usually even in this case, lambda for P MOSFET is regarded as a positive number. So that introduces some changes in our expression for whole PMOS current. For example, if you are talking about P MOSFET, then you have to introduce the negative sign here. So, but I hope that you can easily try and draw your IV characteristics, whether it fits to your insight or your common understanding. So if it is not, then please play with your equations. Then you can have a mirror image of your N MOSFET IV characteristics. So let me just briefly just show different operational regions here. Yes, in this case we have introduced 3 different regions. So one is a cutoff region. It means that there is no current is conducting. So drain current equal to 0. Sometimes I write down in this way for drain current, and sometimes I write down in this way for drain current. So sorry about this confusing notation, but I will try to use capital letter in this course. But please understand, there is no unified way to represent drain current. Capital or just normal small letters are used in literature. Well, anyway, drain current equal to 0 in this colorful region. So if your gate voltage is even lower than a threshold voltage given by some way, for example, let's say that this is happen to be 0.4 volt, and if your gate source voltage is 0.3 volt, it means that regardless the value of your drain voltage, your drain current equal to 0. Why that happens? So think about this one. Here you have applied 0.3 volt. However, in order to collect your electron gases just beneath of this oxide region, then you need 0.4 volt. However, your applied voltage is not sufficient. So simply speaking, you have no electron gas. So although you have a voltage difference between source and drain, but since this channel region is actually isolated or insulated, so you have no current conduction at all. So of course this is quite a crude approximation, but please note that we are now talking about the most simple model, level 1. So yes, so this is quite much limited to this crude expression. Another one is now already our gate source voltage is beyond threshold voltage. Even in this case, we have two different conditions depending on drain voltage. And if we have a relatively low voltage, we are now in the linear region. And if we have a relatively high voltage, drain voltage, then we are in the saturation region, and their drain current expressions are shown here. So if you are quite new to this field, then maybe you are quite much confused with this expression. So let me just explain a little bit more. This equation just says that your drain current is given as the result of evaluation in right hand side term, and here you have some numbers or some symbols which are introduced quite a new way. So this one is just model parameters. You have to specify. The user of a compact model should specify what is the actual number of Kp. Then how about this lambda? Yes, also you have to introduce your lambda value. Then for example, as a user of your compact model, then how can you set this Kp value or lambda value? If you are just a designer, circuit designer, then maybe it's not possible. Instead, your fab guy will provide you this Kp value and lambda value to you, help you design a circuit. So simply speaking, those kind of quantities written with red colors, they are just related with the device itself, so designers cannot change it. Instead, the fab manufacturer should provide these parameters, and collection of these parameters, when it becomes more complicated and sophisticated, then it becomes something called as a PDK. Okay, so of course PDK is much more than that, just a collection of those spice parameters, but this is the basic ingredient of PDK. And let me explain a little bit further. And how about this one, W and L? This is W means that width of your transistor, and L is corresponding to the length of your transistor. And usually the transistor is drawn as just intersection of two different rectangles. So this is the view or top view of a MOSFET. If you just make an intersection between these two rectangles, then the central part, so intersection part, is regarded as channel of your device. Then please, so here we have direction of current flow, and the physical distance or drawn distance between these two lines is corresponding to our channel length scale. And another direction, which is horizontal to the current conduction direction, that is regarded as width of your transistor. it means that although these red colored quantities cannot be changed by designers, however, this width and length, those two parameters can be adjusted by or selected by designers. For example, if you wanted to have shortest length device, then you can draw quite short device. Or if you wanted to have a device with longer gate channel length, then you can draw in this way. If you draw this green box, then your length is increased by increase of this green box. And if you wanted to have wider device with wider width, then what you have to do is just increase the size of this rectangle, then you will have wider device. So this red colored one was were provided from fabrication process, and this width and length, they are provided from our designers. So now we know every quantity we need to implement this device or this expression. You know KP, you know width and length, and one is just a number, and lambda is given from, once again, our fabrication process. And VD, yes, this is voltage, and this voltage is defined as the difference between drain voltage and source voltage. This is typically called as drain to source voltage, means that source is the reference and the measured quantity is the drain. We are now pointing the value of drain with the reference of source. So usually in the case of MOSFET, source voltage is sometimes regarded as 0 when it is grounded. So in some cases people just use in this way, but rigorously we have to use the difference between drain and source voltages. So since we know the value, every voltage of our transistor, we know VD and we know Vs, so this quantity is regarded as a known quantity. And how about this one? Quite similarly, this symbol is called gate to source voltage, and simply it is the difference between gate voltage and source voltage. Yes, since also gate voltage is known to us, so this is a given number. And how about threshold voltage? Threshold voltage can be, for example, can be calculated in this way. So although it is not directly specified in this case, but by using already known quantities, we can calculate VT. So threshold voltage is also known. The other quantity is just the drain voltage and drain voltage. So although discussion was a little bit long, but please have a look at the right hand side of this expression. Is there anything you don't know? There is nothing unknown to us. So although it is lengthy, but we can just evaluate it if we have a good enough computing machine. So we can calculate it this way. Saturation current follows the same way. So we have this expression. So you can also easily evaluate this one. So what we have to do is, first of all, your technology values should be known. Okay, I have lambda, kp, blah blah blah. Yes, first of all, you have to prepare this one. And also from your designers, you have to understand what is the width and length of your transistor. After that, finally, you have to understand what is VGS and what is VDS. When you collect that information all, then you can evaluate this drain current. First of all, depending on these conditions, like whether this is cutoff region or linear region or saturation region, select one of them. After that, just to evaluate it, then you will get drain current, and that drain current will be used to specify the operation of your MOSFET. Yes, so the explanation is a little bit lengthy, but this procedure is quite straightforward. For example, sorry about that. So I think that this page was prepared to give you the expression for PMOSFET, but yes, so I didn't show it to you. Okay, so just move to the NMOSFET example. For example, things looks like this. Kp is given from this number, lambda, and threshold voltage in the zero case is given as this one, and all other parameters have their own meaning, so you can find it in our previous slides. And this is all related with technology, and designers gives us this ratio between width and length, and with these information, so you can now draw in this so-called output characteristics of your transistor. Usually output characteristics of a transistor means that ID versus VDS graph as at several VGS values. For example, you can try draw ID versus VDS at 1.2 volt, 1.1 volt, 1.0 volt of your gate voltages. For example, in this case, this line is corresponding to VGS equal to 1.2 volt, and this is corresponding to 1.1. This is corresponding to 1.0. So you know that if we reduce the gate voltage, then current is reducing. That is quite reasonable. 0.8, 0.7, 0.6, 0.5. Then please have a look at the case where we have exactly at threshold voltage 0.4. What happens? In this case, we are at the border between the cutoff region and turn on transistor, so we have exactly 0 current at here. Okay, so of course you can try to draw this same graph as a homework problem, so please try to do this one. So since this course is so already for graduate students, I'm not talking about why we have these kind of expressions. If you don't understand the derivation of these expressions or physical meaning of lambda or Kp, then please have a look at the lecture materials related with microelectronics. So you have, I think that you had to attend those related courses. Okay, so now here we have output characteristics, and by the way, if we say input characteristics, then usually we say that ID versus VGS characteristics. In this case, we just fix VDS value and draw some lines. That is more important than this output characteristics. But why I don't draw this input characteristics in this case? So usually this input characteristics is typically drawn in two different ways. One is just a linear scale. Linear scale means that when we draw this one, ID versus VGS, sometimes this ID is drawn in its usual normal linear scale, or sometimes we take log 10 of drain current. So however, in our level 1 model, if we are below the threshold voltage, our gate voltage is below the threshold voltage, our drain current becomes identically zero, and you cannot take the zero as an input of your logarithmic function. So that gives us completely wrong result. So I'm just hiding that weak point of this simple model. Of course, in reality, you should not use this kind of too simple model. Of course, you have to have a good enough model to describe the cutoff reason. So, of course, for example, if you go to a model instead of level 1 but level 3, already you have quite good expressions for your drain current below threshold reason, but that is more complicated, so I will not use this one. I will not use that model 3 for educational purpose, but in reality, compact model, although it is called as compact, inside it is quite complicated. Okay, so who feel it is compact? So if you are working as a designer, then you will feel that, oh, this model is evaluate quite fast and compact. But as a developer or implementing guy of that compact model is not simple enough. Okay, then now let's go to the PMOSFET example. So I have not shown you the explicit equations for our PMOSFET. Please take your time and play with your signs to make this graph. If you do it correctly, then you will have this PMOSFET graphs. In this case, usual operation condition is your VDS is lower than 0, and also your VGS is lower than 0. It is because your PMOSFET just operated in that way. This is source of your PMOSFET, and this is drain of your PMOSFET, and usually this source is biased or connected to VDD or something if it is not the case, but in many cases your source voltage is higher than the drain voltage. So when you take the difference between VD and VS, because this is higher than this quantity, usually you have a negative value. Also, your gate to source voltage is negative because source is regarded as the highest voltage we can have. For example, let's just think about this one. Usually, VDD is applied to the source of your PMOSFET, and now say that here you have some quantities. For example, let's say VDD in this technology happen to be 1.2 volt, and you have, for example, 1.0 volt as the gate voltage. Then if I ask you what is the gate voltage, then yes, gate voltage itself is 1.0 volt. However, usually what we want to know is not exactly this gate voltage, but the difference between gate voltage and source voltage. Then if we evaluate it, then we must calculate 1.0 minus 1.2, and it becomes just minus 0.2. So this transistor is biased with minus 0.2 gate to source voltage, although gate voltage itself is in our convention positive, but it doesn't matter. Important one is the difference between them. Source is the reference, and we measure the terminal voltage with the reference of source voltages. Okay, so although I have not shown you the explicit equations for this P MOSFET, that is your own exercise to make these graphs both for N MOSFET and P MOSFET with those given parameters. I will not repeat this one once again. Okay, so today's lecture coverage goes up to the CMOS inverter. So although we have covered N MOSFET and P MOSFET, but it is not that clear how can we implement a logical function out of those two types of transistors. So I will give you the simplest equation. The simplest logic gate is NOT gate. Usually, for example, let's think about this one: X and Y. That requires two different input parameters. However, the simplest one is just not X. It requires just one input parameters and it gives us just the inverted one. So for example, X equal to 0, then Y output becomes 1, X equal to 1, then Y equal to 0. That is a simple expression or operation done by our NOT gate, logical NOT gate. Then how can we implement this simple logical NOT operation? By using our M MOSFET and P MOSFET that is shown in here. This is a schematic of our CMOS inverter, and let's say that V in equal to 0 volt. In this case, please try to calculate first of all VGS in this N MOSFET. VG equal to 0 and source voltage equal to also 0. So our VGS value will be just number 0. So usually our N MOSFET has positive VT value. Threshold voltage is intentionally matched to a positive value. So this device N MOSFET is operated in its cutoff region. So now we say that it does not conduct any current through this drain terminal. And another case is P MOSFET. In this P MOSFET, our source voltage equal to VDD and our gate voltage equal to 0. So when we evaluated gate to source voltage, then 0 minus VDD. So we will have minus VDD as the gate to source voltage of our P MOSFET. So in its absolute value, it is VDD. So it is highly turned on, and we have many holes beneath of this oxide layer. So this one gives us good conductive path between our VDD and output node. So what will be the output of our output voltage of our transistor, our CMOS inverter? Because it provides good electrical connection and it does not provide any electrical connection, so it is just matched to VDD. So simply speaking, when we apply 0 voltage to our input terminal, then we will get VDD as the output node voltage. If we follow the same discussion, then in this case, instead of N MOSFET, now P MOSFET is turned off and N MOSFET is turned on, and its voltage is connected to the ground, and that is called as pulled down. Down means that the voltage close to ground, and up is corresponding to the voltage close to the VDD. Okay, so now what we have to do is now draw a relation between input and output voltage. Well, we know quite clear points. For example, if you apply zero input bias, then there is no doubt that we have VDD as a output voltage. And also, if you insert just VDD as your input voltage, then there is no doubt that the output voltage equal to 0. Yes, in these two extreme cases, we have clearly defined input and output characteristics. Then, how about your input a little bit degraded in the sense of closeness to the 0 and VDD? For example, if you have this input voltage or that input voltage, then what will happen? So now think about this a certain some artificial system like this. Just assume that you have such a kind of relation between your input voltage and output voltage. Then certainly when you have exactly 0 or exactly a VDD, then your system will act as an inverter, logical not gate. However, this green line shows that a system which is extremely weak to the external noise. If you introduce, for example, a slight perturbation to your input, then your output is no longer VDD, but it becomes quite some undefined values. Also, if you have a small voltage perturbation to your input, in this case, then your output will be also degraded quite significantly. So from this discussion, it becomes quite clear that the ideal relation between input and output voltage should looks like this, just a horizontal line. If you have small perturbation, even in this case your value should be just VDD. For example, instead of this 0 volt, if you apply 0.1 volt, but it is still regarded as number 0 and inverted and becomes VDD. So the ideal behavior just looks like this. But how about the actual implementation of our CMOS inverter? So your task is to draw this output and input voltage relationships. That is typically called as voltage transfer curve, VTC, and your homework problem is to draw this voltage transfer curve. Then how about your devices? Okay, it's okay because I have provided model parameters. Please use these PMOSFET parameters and NMOSFET parameters already shown for your PMOSFET and NMOSFET. They share the same parameters. For example, lambda is equal to 0.2 and its threshold voltage is minus 0.4 for our PMOSFET. Our NMOSFET, it has positive 0.4. Okay, so they are well matched technology. Both of NMOSFET and PMOSFET has 0.4 volt as the threshold voltage in its absolute value. Difference comes from their Kp value. Kp value for M MOSFET is much way higher than that for our P MOSFET, but that is corresponding to the reality of our old technology. Nowadays, it's not the case. Nowadays, sometimes P MOSFET outperform the M MOSFET even when we have the same sizes, but for a while, just to consider this older technology. Okay, so that is your homework number 2. And since we have no live streamed lectures in the next week due to my business trip to Greece, so your due for this homework number 2 will be just 2 weeks later. So let me just directly go to this one. Yes, September 9th, 2 weeks later, you have to submit your homework problem. You have sufficiently long time to evaluate it, but before wrapping up today's lecture, I wanted to give you this the principle to calculate this voltage transfer curve. Up to now, I just describe what is this M MOSFET and what is this P MOSFET. They are now described separately. The point is, this system, this CMOS inverter system, is not just a collection of 2 separated devices. They are connected at this point. Their drains are connected to a same point, and that point is regarded as the output node. So what I wanted to say is, how can we calculate the good output voltage satisfying the operation of M MOSFET and P MOSFET? That is shown here. What is the condition for a point on the VTC? For example, let's think about this ideal VTC. We can consider other points, for example here and here, the point on the curve and the point of the curve. What is the difference between these 2 cases? For example, if I ask you this question, if we have this, happen to be this selection of input current and input voltage and output voltage, then is your M MOSFET does not conduct current, or is your P MOSFET conducting no current? So it's not, but the principle that is obeyed by this off the curve point is, for example, let's think about this case. Let me give you a concrete number. For example, let's say that your input is 0.3 volt, happen to be. Then what will happen? In this case, the gate to source voltage will be 0.3 volt for your M MOSFET, and your M MOSFET is completely in the cutoff region. So it means that your M MOSFET says that I do not conduct any current through my drain terminal, so it becomes just 0 ampere. Then how about this one? How about this P MOSFET? In the case of a P MOSFET, the gate to source voltage becomes minus 0.9 volt. So this is, in its absolute sense, quite above the threshold voltage. So now we have whole gas here, and if we have, for example, 0.7 volt as an output voltage. Let's assume that. Even in this case, the MOSFET does not conduct current because that is in its, how can I say, in its cutoff region. And how about our drain? In this case, your PMOSFET is biased in that way. For example, 0.9 volt VDS equal to minus 0.5 volt. Okay, so are you with me? In this case, what will happen? Do you expect zero current of your PMOSFET or non-zero current in your PMOSFET? Of course, all of you agree that if we consider this single PMOSFET, then there will be certainly high current with respect to this well-defined current conduction bias condition. So simply speaking, if we have a certain condition which is not on the voltage transfer curve, then your drain current of a PMOSFET and your drain current of a NMOSFET will not be matched. However, please consider this output node once again. This is your output node and it has only two branches. One branch is the branch connected to your PMOSFET, IDP. Oh, sorry about that. I made mistakes. What is the mistakes? I have drawn in wrong direction. Drain current always should be written in that way. Sorry about that. This is a drain current, and this is your NMOSFET drain current. There is no other branch, no third branch. So since we have only two branches, the sum of two branch current should vanish. If that doesn't vanish, what will happen? If that does not vanish, it means that there will be just accumulation of something that is not possible. So simply speaking, the condition whether a point is on the VTC or not is simply written as this form. Okay. So here I make another mistakes. So equal to no. So I will just correct my presentation material, and this is the expression, the correct expression. Okay, so IDN, sum of drain current of NMOSFET and drain current of PMOSFET should vanish. So now only the point for voltage transfer curve, it will satisfy this condition. So what you can do is quite simple. Try this point. Is this satisfied? No. And try this point. No. Try this point. No. And if you go to happen to be this point, yes, your trial just to satisfy this condition. Yes, the Kirchhoff's current law, then you will get a point in the voltage transfer curve. For example, here I bring one example. When input voltage is 0.5 and output voltage is 0.7, then we have drain current from NMOSFET and drain current of PMOSFET, and as you can see, they do not match that at all. So simply means that the combination of 0.5 and 0.7, this is not the solution of our equation shown here, and it is not on the voltage transfer curve. So please try to do this job. Oh, then maybe you can ask me this question. Oh, there are infinite number of combination, V in and V out. We can have, each of them can have infinite number. Then how can we find good enough voltage transfer curve? Actually, it is not possible to make such kind of just blind test, and if it fails and try another, it's not possible. Instead of that, I want to show you one possible way. Please implement this one. For example, let's think about this one. Let's say our input voltage is given as 0.5 volt, and now our goal is what is the V out value on the VTC curve. Certainly we tried 0.7 volt and we failed. Well, okay, then what will be the next trial? So if you are a little bit educated, then first of all you will ask yourself, should we increase it or decrease it? So please have a look at our previous case. In this case, our NMOS drain current is 1.7 and PMOSFET current is 7.9. It means that PMOSFET conducts more current than NMOSFET. Who should be more stronger, and who should be weaker? Obviously, our NMOSFET should be driven a little bit further, and our PMOSFET should be driven a little bit weaker. Then how can we increase this NMOSFET current? One way to increase NMOSFET current is, yes, if you increase your VDS value, then you will have higher drain current. Why? Please have a look at your output characteristics. So in this case, if you increase your VDS value, you always have increasing drain current. At least it does not decrease. So inspired from this observation, okay, since now our NMOSFET is weaker, then we have to make it stronger. So simply we can say that we will go to the positive way. Then how much we have to go? It really depends on your choice. There is no golden rule, but let me just try certain number, very conservative number, 0.1 volt. Then what will happen? Let me just try 0.8. Previously, we tried 0.7 volt and we failed. And from this observation, the right direction is 0.8. Increase it, and we can have still much imbalanced result, and we can go to further and further. Even in this case, 1.1 volt, still our NMOSFET current is way lower than the PMOSFET current in its absolute sense. And if we go to 1.2 volt, the maximum voltage we can expect. In this case, wow, our PMOSFET now doesn't have any current at all, and NMOSFET now conduct a little current. What is it? Now, how can I say, the balance between NMOSFET and PMOSFET currents are now inverted. Previously, NMOS shows lower current, but now PMOSFET shows lower current. What is this? Now we have to turn to the opposite direction, now we have to reduce this or we have to reduce the output voltage. Well, if you go to, for example, okay, now we have to reduce the current with step 0.1 volt as usual, then what will happen? We'll just ends up with 1.1 volt. It does not give us any kind of improvement. So we need a little bit more strategy. Okay, 1.1 was almost weaker, and we go to 1.2, and now PMOS is weaker. Then what we have to do is, although come back to the lower output voltage, but maybe it is reasonable to try a value in between them. So in this case, I just reduce it by half of our previous step voltage. Previous step voltage was 0.1, and now our step voltage becomes minus sign change, and it's a half value. Well, let me just show you the result. In this case, MOSFET and PMOSFET. Wow, still PMOSFET is stronger. It means that we have to increase once again. But let's say that I just increase once again 0.05. Then what will happen? I will just arrive at 1.2 volt again. It's not that good. So in this case, I just reduce it once again 0.025 volt and increase it. Oh, okay. Now we have stronger MOSFET. Then once again change the signal, and we can keep this way. Try a certain voltage step and check whether the balance is inverted or not. If the balance is, the sign of balance is inverted, it means that our solution is in between our journey. So then reduce the step size and step size, and eventually we will get the value quite close to numerical value, the real solution. I'm not saying that this is analytic solution, but it is good enough in our numeric sense. For example, this is my own implementation result. Here I start again with V in of 0.5 volt, and I start from 0.6 volt. Of course, in this case, it's not that good, so I just increase it. Well, after that, when it arrives at 1.2 volt, now it changes and go to that way. Now the change is invisible almost to our scale, but it is still fluctuating in between, and finally we ends up with this point. So we need 36 iterations to have the error smaller than, if I remember correctly, 1 microvolt. My stop criterion was the voltage change, the step value lower than 1 microvolt, and we need quite many iterations. So anyway, you can try this trial error approach. Then you can try. It was just, for example, a certain gate voltage. For example, it was 0.5 volt. But you can try many other different input voltages. For example, even you can try 0 volt or 1.2. Then what will happen? It will take some iterations, and eventually you will get the converged solution. And my question or homework problem is just to try to draw this voltage transfer curve. As you can see here, it shows really good characteristics. If we have a 0 input and it has 1.2 VDD value, and if we have a VDD value and it gives us exactly 0, and even, for example, even when we have 0.4 volt, but it can be regarded as a logical number 0, and the output becomes quite close to 1.2. It means that this CMOS inverter is quite strong and robust against the fluctuation of input parameter. Wow, that is quite good. And please try to find out the point where your voltage transfer curve meets this line. This line is corresponding to V out equal to V in. So please try to find out a certain point. So sorry about my ugly drawing. So actually we have to find out a certain point, something like this. But anyway, please try to draw your values. Okay, today we have covered quite many things. At the beginning of our lecture today, I just show you binary adder. Why we need binary adder? Because we wanted to make a certain computing system. And we have found that actually basic logical operation is required for our purpose, and that basic logical operation can be obtained from these two types of transistors, MOSFET and PMOSFET. And middle part of our lecture, I have introduced the simplest version of our MOSFET model, level 1 model, and now you have concrete values for your model parameters, and now you can draw IV characteristics of your MOSFET and PMOSFET. And by combining them together, now we can build a CMOS inverter, and the operational condition for CMOS inverter is sum of their drain current should vanish. And now our goal becomes just finding out a solution of this simple one variable equation. However, this one variable equation is a little bit complicated. So without relying on a general methodology, today I just ask you follow this heuristic trial and error approach. Just to pick a point, and if it does not give you sufficiently good answer, then please try to improve your solution. Of course, even the improved solution will not give you the perfect answer, but you are now getting improved, getting better and better solution, and eventually when your error is small enough within machine precision, so the precision of our double precision number or floating point operation, then we will say that, well, although it is not an analytic solution, but we are happy with this numerical solution. So that is the one way to try this one. So I will make an advertisement on lecture 3 and 4. So lecture 3 and 4 will be made just recorded lecture. I will just post my recorded lecture to YouTube channel, so then please watch those videos, and those videos I will give you how can you do it in a more systematic way instead of this trial error way, but you have a more powerful way to solve this system. Okay, so thank you for your attention up to now, and do you have any question? Okay, if not, then I would like to wrap up today's lecture. Thank you, and see you 2 weeks later